Good evening, and welcome to Cozy Sleep Time. Get comfortable and take a slow breath. Let your body relax more and more. Tonight's story is about the birth of stars. Simply listen, or let your mind drift. There is no need to focus. Let the quiet story begin. Tonight we explore the birth of stars, from vast molecular clouds to the moment nuclear fusion ignites a new sun. Stars begin their lives inside enormous molecular clouds scattered throughout the spiral arms of galaxies. These clouds consist primarily of hydrogen gas, with traces of helium and tiny amounts of microscopic dust particles. They often span dozens of light years across and contain enough mass to form thousands of individual stars. Gravity slowly pulls regions of these clouds together, causing them to contract over millions of years. As a region collapses under its own weight, it breaks into smaller fragments. Each fragment is destined to become a star or a multiple star system. The collapsing material heats up as gravitational potential energy converts into thermal energy. A protostar forms at the center of each fragment, surrounded by a rotating disk of gas and dust. Material from the surrounding envelope continues to fall onto the protostar, adding steadily to its mass. The protostar grows denser and hotter at its core as more material accumulates. Temperatures rise over millions of years, pressing inward with enormous force. When the core temperature reaches about 10 million Kelvin, nuclear fusion finally begins. Hydrogen atoms fuse into helium, releasing tremendous amounts of energy in the process. This fusion creates an outward radiation pressure that balances the inward pull of gravity. The young star achieves a stable state called hydrostatic equilibrium. It now enters the main sequence phase, where it will spend most of its life. A star is born, joining the billions of other stars that light up the universe. The smallest protostars never reach the temperatures needed for sustained hydrogen fusion. These failed stars are called brown dwarfs, and they glow faintly from residual heat alone. They never achieve true stellar status, but represent the boundary between planets and stars. Most stars form in clusters, groups of dozens to thousands of stars born from the same cloud. These clusters slowly disperse as member stars drift apart through gravitational interactions. Our own sun likely formed in a cluster that has long since scattered across the galaxy. The Orion Nebula provides a nearby laboratory for observing active star formation today. Its brilliant central region contains young stars still enveloped in their birth material. Astronomers study this region to understand the processes that created our solar system. The Eagle Nebula contains famous pillars of gas and dust where new stars are taking shape. These pillars have been sculpted by radiation from nearby massive stars. Star formation is a slow, patient process unfolding across tens of millions of years. The universe continues to form new stars even as old ones end their lives. Every star in tonight's sky once passed through this journey from cloud to shining nucleus. The birth of a star represents one of the most elegant processes in all of nature. Gravity, pressure, and nuclear physics work together in perfect balance. This balance allows stars to shine steadily for billions of years. And it all begins with a simple cloud of gas drifting through the darkness of space. Once a star settles onto the main sequence, it enters the longest and most stable period of its life. The main sequence phase accounts for roughly 90% of a star's total lifetime. During this phase, the star fuses hydrogen into helium in its core through nuclear reactions. This fusion process releases energy that keeps the star hot and bright for billions of years. The star remains in a delicate balance between gravity pulling inward and pressure pushing outward. Stars like our Sun maintain this balance with remarkable stability over time. The rate of fusion in a star's core depends directly on its mass. More massive stars fuse hydrogen much faster and therefore have shorter lifespans. A star with 10 times the mass of the Sun may live only 20 million years. A star with half the mass of the Sun can burn steadily for 50 billion years or more. The smallest stars, called red dwarfs, will outlast all others in the universe. These dim stars consume their fuel so slowly that none have yet died. The universe is not yet old enough for any red dwarf to have exhausted its hydrogen supply. During the main sequence, the star's size and brightness remain relatively constant. This stability allows planets in the habitable zone to develop and sustain life. Our Sun has been in its main sequence phase for about 4.5 billion years. It will remain in this stable phase for approximately 5 billion more years. Stars produce energy through a chain of nuclear reactions called the proton-proton chain. In this process, 4 hydrogen nuclei combine to form one helium nucleus. The helium nucleus has slightly less mass than the 4 hydrogen nuclei that created it. This missing mass converts into pure energy according to Einstein's equation, E equals mc squared. A tiny amount of mass releases a tremendous amount of energy when converted. Every second, our Sun converts about 400 million tons of hydrogen into energy. This energy travels outward from the core through the radiative zone of the star. Photons bounce from atom to atom, taking thousands of years to reach the surface. Once they reach the surface, they stream into space as sunlight. The energy that warms Earth today was produced in the Sun's core hundreds of thousands of years ago. The surface temperature of a main sequence star determines its color. Hotter stars appear blue or white, while cooler stars appear yellow, orange, or red. Our Sun appears yellow because its surface temperature is about 5,800 Kelvin. The Hertzsprung-Russell diagram plots stars by their temperature and brightness. This diagram reveals that most stars lie along a curved line called the main sequence. The main sequence is not a single path, but a continuous band reflecting different masses. Astronomers use this diagram to understand stellar evolution and measure cosmic distances. A star spends most of its existence in this calm, steady phase of its life. The main sequence represents the stellar equivalent of adulthood. It is a time of balance, stability, and quiet endurance across billions of years. And it is this stability that makes life possible on planets orbiting within the habitable zone. When a star exhausts the hydrogen fuel in its core, it enters the final chapters of its life. How a star dies depends almost entirely on its mass. Stars like our Sun end their lives gently, while more massive stars die in spectacular explosions. When the core runs out of hydrogen, fusion stops and gravity begins to compress it. The core heats up as it contracts, while the outer layers of the star expand dramatically. The star swells to become a red giant, growing to hundreds of times its original size. Our Sun will enter this red giant phase in about 5 billion years. It will expand so much that it will engulf Mercury, Venus, and possibly Earth. The red giant phase lasts only a few 100 million years, a brief moment in stellar terms. During this phase, the star fuses helium into carbon and oxygen in its core. Helium fusion requires higher temperatures than hydrogen fusion. The triple alpha process combines 3 helium nuclei to form one carbon nucleus. When the helium in the core is exhausted, the star fuses helium in a shell around the core. The star becomes unstable and begins to pulsate, losing mass from its outer layers. These pulsations eject the star's atmosphere into space, creating a planetary nebula. These glowing shells of gas expand outward, enriched with elements created inside the star. What remains behind is the star's core. now called a white dwarf. A white dwarf is incredibly dense, packing the mass of the sun into a sphere the size of Earth. A teaspoon of white dwarf material would weigh several tons. White dwarfs are extremely hot when they first form, radiating intense ultraviolet light. They have no internal energy source and simply cool down over billions of years. Eventually, they will become cold, dark objects called black dwarfs. The universe is not old enough for any black dwarfs to have formed yet. More massive stars follow a very different and far more dramatic path. Stars more than 8 times the mass of the Sun develop layered structures. Each layer fuses successively heavier elements, from helium to carbon to neon to oxygen to silicon. The final product is iron, which cannot be fused to release energy. When an iron core accumulates, fusion stops and gravity wins instantly. The core collapses in less than a second, reaching temperatures of billions of degrees. The collapse rebounds in a supernova explosion. A supernova can outshine an entire galaxy for a brief moment. The outer layers of the star are blasted into space at tremendous speeds. These explosions create and distribute all elements heavier than iron. Gold, silver, platinum, and uranium all form during supernova explosions. When the iron core collapses, it may become a neutron star or a black hole. Neutron stars are even denser than white dwarfs, with the mass of the Sun compressed into a sphere only about 10 miles across. If the original star was extremely massive, the core collapses into a black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. The deaths of stars create the chemical richness that makes life possible. Every end is also a beginning, as the material from dying stars seeds new generations. Among the most extreme objects in the universe are neutron stars and black holes, the densest remnants of dead stars. These objects challenge our understanding of matter and gravity. Neutron stars form when a massive star collapses and its core reaches densities comparable to atomic nuclei. At these densities, protons and electrons combine to form neutrons, hence the name neutron star. A typical neutron star contains about 1.5 times the mass of the Sun. Yet all of that mass is compressed into a sphere only about 12 miles across. The density of a neutron star is so extreme that a single teaspoon of its material would weigh about 10 billion tons. Neutron stars rotate extremely rapidly due to the conservation of angular momentum during collapse. A star that rotated once every few days can become a neutron star spinning hundreds of times per second. These rapidly spinning neutron stars are called pulsars because they emit beams of radiation. The beams sweep across space like a lighthouse beacon as the neutron star rotates. When a beam points toward Earth, we detect a pulse of radiation. Pulsars were first discovered in 1967 by Jocelyn, Bell, Burnell, and Anthony Hewish. Pulsars serve as remarkably precise cosmic clocks. Their regular pulses allow astronomers to study gravitational waves and test Einstein's theory of general relativity. Some neutron stars have magnetic fields trillions of times stronger than Earth's. These magnetars emit powerful bursts of X-rays and gamma rays across the galaxy. Neutron stars can also exist in binary systems where they orbit companion stars. When a neutron star pulls material from its companion, the material heats up and emits X-rays. These X-ray binary systems help astronomers locate and study neutron stars. Black holes represent an even more extreme state of matter. When a very massive star collapses, gravity overwhelms all other forces. The core collapses into a point of infinite density called a singularity. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape. The event horizon is not a physical surface, but a point of no return. Anything crossing the event horizon is lost forever from the observable universe. Black holes can be stellar mass, containing 3 to 100 times the mass of the Sun. Supermassive black holes contain millions to billions of times the mass of the Sun. These supermassive black holes reside at the centers of most galaxies, including our Milky Way, Sagittarius. A star is the supermassive black hole at the center of our galaxy. It contains about 4 million times the mass of the Sun. Black holes cannot be directly observed because they emit no light. Astronomers detect them by their gravitational influence on nearby stars and gas. In 2019, the Event Horizon telescope captured the first direct image of a black hole's shadow. This image showed the supermassive black hole at the center of galaxy. It confirmed predictions made by Einstein's general relativity over a century earlier. Gravitational waves from merging black holes were first detected in 2015. These ripples in space-time open a new way of observing the universe. Neutron stars and black holes represent the ultimate fate of the most massive stars. They are cosmic laboratories where the laws of physics are tested to their limits. The stars that decorate the night sky display a beautiful range of colors, from cool red to blazing blue. These colors are not random, but directly reveal a star's surface temperature. The connection between color and temperature is a fundamental principle of physics. A hot object glows with shorter wavelength light, appearing blue or white. A cooler object glows with longer wavelength light, appearing orange or red. This relationship holds true for stars, just as it does for a piece of heated metal. The hottest stars have surface temperatures exceeding 30,000 Kelvin. They appear blue or blue-white and are called O-type and B-type stars. These stars are extremely luminous and burn through their fuel very quickly. Rigel in the constellation Orion is a famous blue supergiant star. Stars with surface temperatures around 10,000 Kelvin appear white. Sirius, the brightest star in our night sky, appears white and is an A-type star. Our Sun has a surface temperature of about 5,800 Kelvin. It appears yellow and belongs to spectral type G. The coolest stars have surface temperatures below 3,500 Kelvin. They appear red and are called M-type stars. Betelgeuse in Orion is a famous red supergiant star. Astronomers classify stars using the spectral sequence O, B, A, F, G, K, and M. This sequence runs from hottest to coolest and is memorized with the phrase, "Oh, be a fine girl, kiss me." Each spectral type is further divided into subclasses numbered from 0 through 9. The spectral classification system was developed at Harvard College Observatory in the late 19th century. Women astronomers, including Annie Jump Cannon, made crucial contributions to this work. The system is based on the absorption lines present in a star's spectrum. These lines reveal not only temperature, but also chemical composition and motion. A star's spectrum acts like a fingerprint, uniquely identifying its properties. Different elements absorb light at specific wavelengths, creating dark lines in the spectrum. Hydrogen lines are strongest in A-type stars and weaker in hotter and cooler stars. The color of a star also depends on the amount of dust between the star and Earth. Interstellar dust scatters blue light more efficiently than red light. This causes distant stars to appear redder than they truly are. This effect is called interstellar reddening and must be accounted for by astronomers. The brightness of a star depends on both its temperature and its size. A cool star can appear very bright if it is extremely large, like a red supergiant. A hot star can appear very dim if it is extremely small, like a white dwarf. The Hertzsprung-Russell diagram plots stars by spectral type and luminosity. This diagram reveals distinct groups including the main sequence, giants, and white dwarfs. The color of a star can be appreciated simply by looking at the night sky. Orion's two brightest stars show this contrast beautifully. Betelgeuse glows red, while Rigel shines blue in the same constellation. With binoculars or a small telescope, the colors of stars become even more apparent. Albireo in the constellation Cygnus appears as a beautiful double star with contrasting gold and blue colors. Each star's color tells a story about its temperature, its size, and its stage of life. The atoms that make up our bodies, our planet, and everything we know were forged inside stars. This remarkable fact connects every human being to the life cycles of stars across cosmic time. The process by which stars create elements is called stellar nucleosynthesis. It begins with the simplest element, hydrogen, which was created in the Big Bang. Stars act as cosmic factories, transforming light elements into heavier ones through nuclear fusion. Hydrogen fuses into helium in the cores of main sequence stars like our Sun. Helium fuses into carbon and oxygen in red giant stars. Carbon can fuse into neon, sodium, and magnesium in more massive stars. Neon fuses into oxygen and magnesium in the next stage. Oxygen fuses into silicon, phosphorus, and sulfur at even higher temperatures. Silicon fuses into iron, nickel, and elements near iron on the periodic table. Each stage of fusion occurs at higher temperatures and pressures than the last. Iron represents the end point of fusion in massive stars. Fusing iron requires energy rather than releasing it, so the star's core collapses. This collapse triggers the supernova explosion that disperses the star's elements into space. During the supernova, intense neutron bombardment creates elements heavier than iron. Gold, silver, platinum, lead, and uranium are produced in this rapid neutron capture process. This process is called the R process, where R stands for rapid. A slower neutron capture process called the S process also creates heavy elements in red giant stars. Every carbon atom in your body was fused from helium inside a red giant star. Every oxygen atom you breathe was created by stellar fusion. The calcium in your bones and the iron in your blood originated in stars. The nitrogen in your DNA was produced through stellar nucleosynthesis. Even the gold in jewelry was created in a supernova or neutron star collision. In 2017, astronomers confirmed that neutron star mergers also produce heavy elements. The collision of two neutron stars was observed through both gravitational waves and light. This event confirmed that neutron star mergers produce gold, platinum, and other precious metals. The elements created in stars are distributed through supernova explosions and stellar winds. These enriched clouds of gas and dust eventually collapse to form new stars and planets. Our solar system formed from material enriched by many generations of stars. The Sun contains about 2% heavy elements by mass. The planets, including Earth, formed from the heavier elements in the protoplanetary disk. Life emerged on Earth using the elements provided by stellar nucleosynthesis. This chain of cosmic creation stretches across billions of years. The atoms in your left hand and your right hand likely came from different stars. We are collections of stardust, temporarily assembled into conscious beings. Every breath you take contains atoms that were once inside distant stars. When stars die, they give their material back to the universe for new uses. This cosmic recycling ensures that nothing is truly wasted in the universe. We are part of an ongoing cosmic story of creation, destruction, and renewal. As our story ends, let the quiet ideas settle softly. Your body can continue to relax, breathing slow and steady. If sleep is near, let it arrive naturally. Thank you for spending this moment here on Cozy Sleep Time. Return anytime for another peaceful journey. Good night.